Hi, in this video, we want to take a look at further methods for handling spatial data. All right, so what we're talking about in this one really is more akin to like set theory than handling data. So we're going to be interested in taking a look at things like the union of different spatial data items or the intersection of spatial, spatial data. Ways to check to see is there an overlap, ways to check to see if there's a hole, things like that. All right, so this code is modified from the website for applied spatial data analysis with R. Here is the website where I got this from. The textbook can be downloaded for free through UCS library. So if you're a student, you can go get it easy peasy lemon squeezy. All right, so I'm copy and pasting to a large extent this code from the author's website. And the author says that we need these data sets to be able to run this code. Now, there's some other data sets that are needed that are in R that the packages have that we just need to use the data function to pull up. All right. And I've modified the code so that things just go along with how I like to do my naming conventions and how I like to use keywords and things like that. Okay, so the first thing to talk about is support. So when you hear support, really that's referring to the area that is under consideration with our spatial data. So in a sense, it's kind of like support in like market basket analysis support. What we have supporting our model data-wise. All right, so here's an example. Let's look at topographic information on Auckland's Mangawahu volcano. Okay, so it's one of 50 volcanoes in Auckland's volcanic field, and this data can be loaded from base R's datasets package. So I just go through, I load the data. It's already available in R, and here I'm using the str, the structure function, to take a look at what I've got, so I know what's there. And we can see that we have. This looks like, we could think of this as a matrix with 87 rows, 61 columns. Now, something about this is that the author multiplies all of the X and Y values by 10 and to get us a grid. So this indicates how far apart the grid points are. Then the author sets up the terrain colors, which is a base R function, and then goes through and builds up the image. All right, so what we have our, now something that's interesting to pay attention. If you look at the author's code, what is called Y is X, what's called X is Y, by what the author put in, because the author put in Y first, then X. And so I just labeled it the way, the author didn't use keywords. I put that in there. And then here, the Z, you'll notice that there's a transpose going on. And then there's a reversal of the column order. And then the breaks are the sequence from 90 to 200 by 10. Then we're coloring it by the terrain colors we had, and we're putting on aspect ratio 1. Remember, that's always important. All right, so what will happen when I'm plotting something with default statistics plotting, it's always going to try and take up the entire space so that we can get like a better view of the data. That's the base, the base statistics way of plotting. When I'm doing something with spatial data, I don't want that because I need to keep that ratio correct. Otherwise, we could have like the state of Florida looking like really, really, really wide. And this is just saying don't put the axes on. So let's take a look at what we get. Okay, so something that is important for what's going to happen in a moment, look at how granular this looks. You notice how everything, we see all these right angles and straight lines. Do you think the actual elevation goes like that? Looks like stair steps? No, pretty sure that's not what's really going on. So the point of this visualization is to demonstrate that we only have like a certain level of granularity in our data. We can only know so much about it. Now, let's look down here. What I'm going to do next is, I don't want to show the punchline. I'm going to take contour function in base R once again, my X and my Y, transpose, level's the same, aspect ratio, axes, everything's the same, except instead of image, and with colors, I'm using a contour plot. Now, let's take a look at what we got. Doesn't this look a lot smoother? Don't these lines look pretty smooth for like the boundary between elevations? So, you know, what this is saying is that every point along this line is at 110 meters above sea level. Every point along this line is 130 meters above sea level, and so on. And we have the corresponding information. If we were to take the colors and connect back to elevation, we have the same information in the previous slide or the previous image. Now, they're the same data. Okay, so what's going on here? This is actually what we have. This is truly what we have for our data. This is our best information that's going on. But when I pass it to this algorithm, you can see that it went through and made it look a lot smoother than the original data has. And so this, you know, intuitively, this looks a lot more like what I would expect to see on the ground. But, you know, there's a gap between the ground and my data and my map. And so by kind of filling in things, making it smooth, I get the impression that I have more precise information than I really have. Here, it's very clear, like, you know, how coarse my data is when I look at it this way. But here, it feels like I have much more precision what's going on. So this is something to be mindful of as we do our visualizations, as we reach our conclusions, is that just because it looks really good doesn't mean it's better than what you really have. All right, so now let's start taking a look at handling and combining features. And we're going to look at the RGOS package. So this is, you know, in R, handling like geometric, geographic operations. So geometric operations on geographic data. All right, so this paragraph is out of spot, but the get scale and set scales function are used to get and set the scale options in the RGOS environments. So this is used to determine the precision of the coordinates when translating to and from you know, objects in this package. So precision is defined as 1 over scale. So remember, in statistics, usually we'll say precision is 1 over standard deviation or 1 over variance, depending on which textbook, which author you're talking about. So here, let's go ahead and get scale. So this is going to be the default scale in R. And so we can see that it's 1 times 10 to the power of 8. Now, this part of the code is what the author put in, that this is an option to set do poly check. So here I'm saying don't do polynomial checks on this. And let's see. So this paragraph, the internal GEOS representation defines a polygon object as a collection of only one exterior ring and from 0 to many interior rings. So an SP polynomials object corresponds to a GEOS multi-polynomial object. So this is important as we go back and forth between different object structures in R, but without proper hole assignments. And the default for do poly check is true. If we set it to false, polygon objects is not valid in geo terms. And so good warning, geos may crash R, which is why checks are imposed by default. So that's something to be mindful of. So if you're going to be working with the RGOS package, basically this is just saying, this is from the help documentation, by the way. Make sure that you're just saving your work as you go. I'm not familiar with this, the test package RGOS. I did not find anything on here. It was in the author's code. And here I'm setting the do poly check back to true. All right, so now let's start getting into using RGOS. And here we can use the set repels coordinates warn to turn off warnings. It's just because, you know, as you work through this, you keep on getting all these warnings that get kind of annoying. We can turn it off if we just set it to false like we do here. All right, so now let's actually start working on an example. What we're going to do, we're going to take several spatial data sets for a city in Brazil. This is a historic city. You can look it up on Wikipedia or Google Maps. That's what I did before making the video. And it looks like an interesting place to go. I'm not going there in this video though. But we're going to take information about Olinda, Brazil, and we're going to be taking multiple spatial data sets and working with them in different manners. All right, so first and foremost, let's go ahead and load the shapefile for Olinda, Brazil. And I'm going to go ahead and call this as Spatial Polygons Data Frame Olinda 1. The reason why I name it this is because the object is a spatial polygons data frame. So I have spatial polygons connected to a data frame. Here's the layer that I'm taking from the shapefile. And I'm going to go ahead and allow a loss. And that's just so that we can process things. So we need some flexibility in making sure that different files will work together. So I'm allowing a loss. All right, and we get a warning about unknown projection definition. And we can see that we have 470 features and 6 fields. All right, so now let's go ahead and set our projection, or actually let's set our coordinate system, is a better way to say it. And we're going to go EPSG 467. And according to the author, this is a good one for that region of the world. All right, so now let's just do a quick plot, see what's going on. So I'm going to use the spplot function in the sp package, since it's a spatial polygons data frame. And we can see, boom, remember I had 6 fields, and we can see that those fields are like code, geo, code B, in Blair, bear, V014 ID, a different code geo, code I, and then TIPO. My dog is trying to get in. All right, so now let's actually go ahead and switch to a better projection. So what we're going to do is this is one that the author said that is actually a better one to work with. It's very common for this area of the world to use. And here's the information that I've got. So this, remember, the make EPSG, this function gives us information about different projections that we have available to us in the RGDOL package. And so I looked it up beforehand. I found that it was row 3177. So I went ahead and just grabbed it, because there's no row name, so you just use the row number. And here's its information. Here's its code. Here's its note. So you notice it's UTM, zone 25S. Here's its projection information, and it's transverse Mercator. All right. So now what I'm going to do, I'm going to transform what I had into this projection. So what was going on is that the data was originally saved with the previous projection. Now I'm using SP transform to get a better projection for the work that we are doing. And notice that to do this, I'm just specifying the code with this information here. So I'm just putting 31985 here. And let's go ahead and just plot it again, see what happens, see what looks different. So let's take a quick look. And to my eyes, I don't see much of a difference. It honestly probably wouldn't make much of a difference if we proceeded with, as is, but yeah, we'll keep going. And now I'm going to return the warning setting to true. All right, so now let's look at the area of geometry. So now what we want to do, we want to calculate the area of different geometric polygons. And so to do that, we're going to use the G area function in RGOS. So here, I take my spatial polygons data frame, and what is going to happen here is it's going to go through all of the polygons and compute the area. And so there's a bunch of them. Remember, there are, let's see, how many? Let's look back up. There are 470 polygons, and that could be, those polygons could be broken up in something like islands or broken up districts. But there's 470 of them. So rather than looking at 470 numbers, I went ahead and just put it in a histogram. And so the thing that jumps out at me very strongly is that clearly this is a skew right distribution. We have a few that have a lot, a large area compared to the rest, and then the vast majority are in this range here. All right, so now what I want to do, I want to get the area, and I want to store that on my data frame. So what we're going to do, I'm going to use the slot function. So I'm going to grab the slot for each of the polygons. So I'm grabbing this object and I'm saying go to the polygons slot of the object, grab that. Now, once I get the polygon, each polygon has information about it. I'm saying grab the area of that using the slots. And now what I'm going to do, I'm going to check to see, is that the same as the G area calculation? Let's find out. All right, so what is going on is that my spatial polygons data frame had the area already for us. I could have just gone ahead and grabbed it, or I have the option of computing it. Well, if I had a data set that didn't have it computed for me, I would need that G area function. So just to see, is everything kosher? Is everything looking good? We're going to check to see, are these actually the same? So I'm going to take my G area calculations, and I'm going to compare it to the areas that I got from the polygons that are stored in the spatial polygons data frame. And yes, we can see with the all equal function that they're all equal. So it's good. There's an agreement. All right, so here, the author didn't say what this calculation is. I think it's population density because this data set corresponds to census data. So what we're doing here is I'm taking this number, which I believe is number of the population number. I don't actually know, I'm making a guess. Then I'm dividing by the area. And then I believe that this is rescaling for this being in a million people. 2 million. Yep. And so let's see what happens. All right, so we can see that we can get a histogram looking at the population density of each of our polygons. So something that is interesting is how we have a few that are skew right for polygon size, and we have a smaller number are skew right for population density. So we definitely do not have like an even population distribution. All right, so now let's go ahead and now I've got this, let's look at the quantile for population density. So I'm going here, and the author chose to go from 0 to 1 in steps of 20. And so here's the lowest, here's the highest population density, and we can see that the middle is in this region. All right. So now let's go ahead and plot the population density of Olinda. So I'm taking my spatial polygons data frame. I'm going to say that the density, population density, is my Z. And then I'm going to chop things up there. Here, I'm going to define the colors I'm going to use. So we're going to have 1, 2, 3, 4, 5 bins. You notice that 6. Drop in the first one, there's going to be 5 different colors. We're going to throw in some gray in there also for a boundary. Here's our line width, and then we're keeping our color key. So here we go. And so here we go. We can see where we have a larger population density pretty easily. So this is kind of interesting. Like there's not very many people in these areas. Like this one I find very interesting. Since it's such a high population density, then no one over here. It'd be interesting to look at why. Probably has to do with like the history of the city. Okay, so now what we want to take a look at is what do I do when I have multiple polygons or multiple spatial data sets that I'm working with, and what can I do? So here we're going to look at geometry union, and so what we're going to do, we're going to take 2 geometries, put them together into one spatial polygon. All right, so here I'm taking all the polygons from this and I'm putting it into one big polygon. So all of the little polygons that we saw a moment ago with the different colors of yellow and red are now just going to be one big region. And let's compute that area. And we can see that's much larger than the other areas we had previously because it's all of them put together. All right, now let's go ahead and get the area of the polygons. And you'll notice what ends up happening is that I've got one big one, then all of these are within machine accuracy of 0. So there's just one polygon going on. So let's go ahead and plot that. And we can see these little specks here. These are probably like holes in the data set, holes in the geometry, maybe some lines, something like that. And that accounts for these little tiny numbers that are off by themselves. So here's what there's 6 of them. So 1, 2, 3, 4, 5, 6. Boom. We got it. Now we're going to test to see if the geometries overlap. Okay, so this function, the G overlaps, checks to see, do we have any geometries overlapping each other, on top of each other? This is important to know because if I start plotting them, I want to know, is one blocking the other on my map? Now I look here, we know that these guys are on top of the big one. Therefore, we know it's going to be true. And boom, we got it. All right, so let's go ahead and set our scale. And we're going to do our overlap. And now notice that I've reduced the scale by quite a bit since I've reduced my precision. Now, when I run the overlaps function, I get false. So I'm not seeing any overlaps on this scale anymore because those other ones were so tiny that they wouldn't even be detected. And now here, what we're doing the same thing to a large extent. Is so the O scale a moment ago was the default scale that I had set. So I saved it before I changed the scale. Now I'm changing it back. And here I can get my area. The lesser precision scale could have resulted in a less accurate number here. And now the upcoming code is going to probably throw some warnings. So the author went ahead and put it to false for the warnings. So now let's read in some more data. All right, this time we're going to use the L7 ETM8S TIFF file. And we can see that we have 704 rows, 698 columns. And it's griping about the projection. So let's go ahead and set it to the one that we want. So what I'm going to do, I'm going to take the object I'm going to be working with. I want everything to have the same projection. So instead of like figuring out what it is, I'm extracting it. I extract the projection. I set that to the projection I want. And I say that's the projection for the object I'm going to be working with. Easy peasy, lemon squeezy. Now let's load another data set. This is L7 ETM's TIFF, and we're going to call this TM. The previous one we called PAN. And I'm using the same trick to define the projection string. So I'm taking the object whose coordinates I want to use. I grab its projection string. I set the coordinate reference system to be the projection string of the object I want to work with. And let's go ahead and get the names of our TM objects. And this is going to be TM1, TM2, 3, 4, 5, 6, 7. I believe these might be principal components or something like that. One of the data sets of principal components. I don't know if this one doesn't really matter what it is, where it came from for our purpose, because we're just trying to look at how to handle geographic data. And then here, let's load some more data. So this is Olinda DIM, demographic information, UTM 25S TIFF. 11 rows, 11 columns. Now, something that should be jumping out at you is like, hey, we have different rows, different columns. How are we going to combine that? You're going to find out soon. And once again, I'm going to set the projection string exactly the same way I did with the previous two. All right, so now what I'm going to do is whenever we have a missing value, so I'm going to take the values that don't make sense. So it's less than or equal to 0, which doesn't make sense for this type of data. I'm going to say, hey, that is a missing value instead. So this is an unusual way of defining missing value. And now let's go ahead and plot our TM objects. And so we get to take an interesting look at the Olinda city. Now, remember, these are default colors. These are default colors to go, from yellow to dark. There's, this color palette is pretty good for the purpose of like people who are colorblind. It's also good that, the bright is on one scale, dark is on the other, and color of the rainbow goes along the scale also. So people will actually do a better job judging what they're looking at, but these are definitely unnatural colors to be looking at. I wouldn't use these professionally. I've definitely use these while I'm working on it, but before I give it to my stakeholders, I would choose a different color palette to be more informative with what we're looking at. Now here we have dim. We plot that. So here you can see that we have, you know, a map going on, and we've got some missing values in here. And we can see that there's some missing values in this also. Now we're going to turn on that warning again. And then the author turns it off. Don't know why. Now this upcoming chunk of code, I wasn't able to find this file anywhere, so I just skipped over this code. This chunk was not ran, but here is the SP grass 6 package to work with, and it looks like it's got some utility to it, but without the file, I don't know what to do, so I just skipped it. All right, so now let's go ahead and load some stream data. So let's get the shape file for streams in Olinda. I'm using RGDOL package, read OGR. And it's going to be a spatial lines data frame. We're going to represent the streams, the water, with spatial lines. Now I'm going to go ahead and set the projection. And now let's go ahead and plot it. And so now we can see cat, value, and label. And we can also see where are the streams in the city. So we can look at the number of rows in there. So we can see how many streams we're talking about. Get summary statistics of our data. Now, next thing we want to ask ourselves, when I'm looking at two spatial data sets, do they touch? Is there any connection between them? Are they completely separate? Not only are we interested in like overlaps, we're also interested in, do they connect? Is it going to be like Florida and Georgia where they do connect, or like Florida and New York State where they don't? Okay, so we're going to use the G touches to check to see, do they touch? Now remember, scale can change the answer on this for yes and no. If I have a coarse enough value, I can get true. If I go super fine, it's possible to get false on the same data sets. So be mindful of that when you set your scale. So next we want to convert a square spatial matrix to a weights list object. And to do that, we're going to use matrix to list W. So we're taking a matrix, converting it to list weights, weighted list. And so I'm taking the GTouch streams outputs that we have here. So the output here is going to be a matrix indicating if two polygons touch, yes or no. And then this is converting it to that weighted list. And now here we can go through and we can look for searching neighbors by going by which ones touch, which ones don't. And so here we see that we can have the, we've got 21 like connecting neighbors. Now, next one that we want to look at is another union, but this time we're doing it on lines. We're not doing it on polygons, we're doing it on lines that we want to put them together. So I'm going to take that spatial lines data frame, and I want to merge them all into just like one big body of water. I'm going to use G-line merge to do that. And we see that we end up getting 21 distinct streams. And we can get our summary statistics off of that also. And you'll notice that our spatial lines length is equal to what we get off of that G length computation. And so now let's go ahead and plot it. And so we can see that we have some individual streams here and there. Now these are all connected, been merged into just one big stream. So we don't know, like we can't figure out the direction necessarily. You know, we know where the ocean is, so we probably could work out some details, but you know, so we can see the distinct bodies of water that don't connect to each other off of this map. Now, next thing we want to take a look at is geometry intersections. So if I have two different geometries, maybe I'm interested only in where they overlap with each other. And to do that, we're going to use G intersection. Okay, G, then whatever operation I want is the convention in RGOS. It's kind of nice. And so I need two sets to be able to do the intersection. So I'll do spatial line stream and spatial polygons data frame for the Olinda with the second projection on there. And we can see that when I do this, so what I'm doing is I'm taking polygons and I'm taking lines, I'm taking the intersection, I end up getting lines. All right, so as you do this kind of thing, you know, if I had polygons and polygons, it's possible that if they overlap like this, I get that middle polygon. If I have polygons and their borders intersect, then I'll get a line, or if they only touch, I could get a point. So when I do this, different polygons or different spatial objects mixed together will give me different classes of geometric objects. And so on this one, we get spatial lines because I'm taking lines that are really contained for the most part, maybe not necessarily, but a good portion of them are contained inside the other polygon data set. And so now let's take a look. All right, so that's how many of the original streams are left after the intersection. And let's go ahead and plot it. And notice that I'm using regular plot on this one. I wasn't able to get SP plot to work with this, so the colors didn't come out. And so this is what's left after I take the intersection with the polygons. And you know, this is just demonstrating aspects of like the number of rows, the information that we have on each stream. And here, you know, we can compute the lengths of our spatial lines. And something we can do, we can use tapply, that I'm taking those lengths, I'm taking the index from the intersection on the streams, and I'm adding them up. And so then I ultimately get some new information about those combined you know, bodies of water. All right, so now here are some experimental functions that are in RGOS. So G unary str tree query and G binary str tree query build input envelopes by disregarding topology and reducing the coordinates to a multi-point representation. Okay, so these build envelopes by ignoring the topology structure that's already established, and then reduces the coordinates to multi-points. And so this permits the trees to be built and queried even when some geometries are not valid. And so if you want, you can dig into these. I haven't used these professionally, so I don't really have much to say about these. All right, next one, buffer geometry. So let's say I want to take objects I have and I want to put a buffer around them. Well, the G buffer function will do that for me. So what we're going to do on this one, we're going to take our bodies of water. We're going to put, so you know that they're just lines. Well, what if I go, you know what? I'm dealing with some pretty big bodies of water. having just a line doesn't make sense. You know, if I've got a big river, big canal, something like that, having it as a line doesn't do it justice. It's bigger than what it looks like on the map. Well, what I could do is I could put a buffer around it so it looks wider, it looks bigger on the map, so I get a better representation of what's actually there. All right, so what we're going to do is with the G buffer function, I'm going to put a width of 50 on there. And then when I plot it, I can see the same bodies of water, but now I've got some space between where the line was. So the lines were originally in the middle, and it just kind of put a buffer around it. So now it looks like an actual flowing river instead of a brook or a stream that I could step over. And of course, we can compute buffer area. So what I need to do is just figure out the polygons, and then I can compute it. And so we can go through and we can do some intersections. And so you'll notice that in this intersection, so even though this is inside the geographic region we're dealing with, there is a limit to the precision of our data. Because of that limit in the precision, we can see that parts of the buffer rivers that should be there are not there because there's a lack of precision in this data set here, unfortunately. And these are just like playing around, digging into what we get. You know, so this part is working into computing the area of our buffered geometry regions. And so now we can, so I have the option of adding on to our spatial polygons data frame by just treating it like a regular old data frame. And when I plot it using SP plot, you'll notice that it gets plotted immediately for us along with the others. So now let's take a look at which streams are actually inside the city of Olinda. So those streams were taken and they're in the area of Olinda, but they're not necessarily in the city boundaries. Now I want to look at only ones that are inside the city boundaries. So we're going to do G intersection. I'm going to take the streams, and then I'm going to say do the grab everything that's inside that big polygon. And so when I plot it, I can see this is all of the streams that are inside the actual city limits. The other streams that are outside that we plotted previously are in the area of the city, but are not properly inside Olinda. All right, now, so let's go ahead and plot another variable that we created. This time we're going to use the Brewer palette function to just get blues, and we're going to get 5 of them. So I'm taking my spatial polygons data frame. Here is the variable from the data frame that I want. I'm saying that, and this color palette actually returns a function. So this is a function for returning colors. I want 20 different colors, and we're going to add transparency to the background. And then our layout is going to be a list. So this is a specialized list in R, and we want SP lines and stream inside for my layout. And then my color key we're going to put to the right, and this is the size of the labels, and we're putting a width of 1. And we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different colors. Oh, not exactly what I thought it would be, but because I thought it would be 20, but all right. So here we get, kind of a more interesting representation of the rivers of what's going on. So here we use that that buffer geometry to kind of figure out maybe like what's deeper, you know, where the bigger rivers are. All right, let's look at map overlays or spatial join. All right, so spatial joins are just like are typically going to be like left joins in with spatial data. So when I do map overlay, think of it as I'm doing a left join. The first one, I keep everything, but in the second data set, anything that's not in the region of the first gets kicked out. So we're going to use the MeUse data from the SP package. Going to set the coordinates. MeUse grid, do the same thing. Now let's go ahead and plot. And so we can see, here's the MeUse data set. Unfortunately, each of these variables are on different scales, so we really can't see what is going on. Now let's look at the grid. So we have some more information. Now what I want to do, an over function on this. So to explain this, I want to look at the plot that we're going to have. So here is my MeUse data sets. Okay, and okay, let me back up. All right, what's going on? I'm doing over in the SP package. Think of this as a left join. So here, this is my left data set. This is my right data set. What's going to happen is everything in here that is inside the coordinate set of this data set is going to be kept, and it's going to be appended onto this set over here. And then we're manipulating things so that things work out, and you'll notice that everything looks really much like it did in the original MeUse plots. Now, next thing we can use, or something that's also good, is for being able to do spatial aggregation. So let's say that I have data points over a region, and I want to take the average by region. And when I say region, along a grid. All right, so I've got a bunch of data points. What I want to do, I want to establish a grid where at each grid point, the proximal data points are average, summed, max, min, something like that. All right, so first I need my grid topology to specify where are the centers of each of the points I want to have when I'm all done. Then what I'm going to do, I'm going to take my data, I'm going to start aggregating either a maximum, minimum, median, mean, something like that. So here, this specifies where my final grid points will be. I'm establishing my spatial grid. Now let's go ahead and plot that. And so here's my grid that I'll actually have. Now what I want to do, I want to go through, I want to take the max for zinc and lead over each of the grid squares in my spatial grid. Let's see what happens. All right, so here, this is the actual grid itself. We get summary statistics, and let's plot it. And so now we can see, so the X's are where the actual data points are, and the colors represent the max for each of the squares. So I know the max of the X's of the data points in this square are much greater than the max here or the max here. So this is where this is a maximum color. So I know the maximum on the data set is here. And so this is the aggregation. So each of these squares is my grid. Each of the data points inside the square, I apply minimum, maximum, median, min, whatever it is I want, maybe sum, whatever aggregate function I want, I apply it to all the data points in this square, and that determines the color of each of these squares. All right, the next thing that we want to take a look at is normalize the difference vegetation index. All right, so what this does is takes the difference in light measured typically from a satellite with red and near red infrared, and then it's like a difference and addition and division, and that usually is used as an indication of the amount of foliage in an area. So let's go ahead and take the TM data set that we've got, which has the light information that we need. Let's save it as a spatial pixel data frame. Then I'm going to take the part of this that corresponds to that union that I did earlier. And then let's go ahead and do principal component analysis on TM1. And this is just converting into a data frame so that it makes sense to be able to do this. I'm only taking the first 6 columns. Now I'm running the predict function to get the principal components. And then I am getting just the first 3 out of it. And now this is just to plot the first 2 principal components. And I'm choosing my color palette the way I want to. This specifies the layout and how I want my color key to appear. And so now I can see my principal components, where green is the lower values and the red, pink are the greater values for each of these. And this, remember that the over function is working to do a left join. So I'm taking this and I'm doing a left join on the region. So I'm taking the principal component values for each of the locations on the map that are included in the Olinda data sets. And here I'm doing a spatial column bind on that. And notice that we set up the row names for the O mean. So here, O mean is the left join. Set up the row names to make sure things match up the way we want to. So here, grabbing the row names here for O mean, and then I'm doing my column bind. And by setting up the row names, I know I'm going to get things to line up the right way. And so here we can see what the plot would be. It doesn't look very informative. And I can use over also to perform aggregate functions for us. For like here, for this example is median. The default is for mean, to take the average over regions as, you know, so the reason why we need this is if, let's say I have a point here on the left asset, several points near it that correspond to it. Well, how do I take these multiple points and connect to these ones? So this one data point, let's say I'll point it here, has multiple points within scale in the right data sets. In some way, some shape, some form, we need to take these and connect it to this location. All right, so what's happening is the default is to take the average. That makes perfect sense. That's, you know, how, you know, that's a very good default. If I want to, I could go with median, I could go max, I could go sum, I could do any way I want to go with an aggregate function. Here we're choosing median, and we're going through and doing things very much the same way. Here I'm doing sum. And I can, you know, get these values also in my plots. And so the next few examples that are in the document are very much like repeats of just doing this with different data, with different data sets and slightly different techniques, but really morally, this is getting, I feel like it's getting redundant. So I'm going to go ahead and accelerate past it. If you want the original file, I'll give it to you. You can get it from the author's website also. We can also use rasterstack to get information out of our data. So if I take TM1 and I use rasterstack, we can see that it goes ahead and it gives me a pretty good looking data set. I like the default settings on this much more. I have my scales going on. Now things are smaller, so it's harder to see, but I can feel this feels like it's much easier to interpret, figure out what's going on. And we can use the extract function to extract. And so here, I've got the raster objects. I want to take the SP objects and I want to extract features to match up with the raster object. And so this is similar to that left join mentality. And this next part is just checking to see if our computations using raster match the previous techniques that we use, and we can see that they're matching up nicely. So it doesn't really matter how we approach it, which tool, we'll get the same output either way. Now, the next thing that we want to talk about is spatial sampling. So sampling, so what I've got going on is I've got my data. I might want to do some random sampling. There's, I believe, 5 different ways to do this. Of course, random sampling is the most well known. There's grid sampling, cluster sampling, stratified sampling also. And these all make sense in terms of polygons. So if over my polygon region, I can do, cluster sampling, I can do stratified sampling, I can do random sampling across all the data sets. And it's pretty much exactly what you expect. So here, the function for that in the SP package is SP sample. And then I specify my geometric objects, how many things I want to sample. Now, notice that this is going to be with replacement, and I do random. And so, all right, so this one's random. Here is a regular sampling, and of course, like once we get this, we can do, it becomes a geometric object, and I can use all the other functions for working with this like I did before. So let's go ahead and start doing some plotting just so that we can see what's going on. Here is our random sampling. Here's our grid random. And this is grid regular. And we can take a look at the empirical cumulative distribution function. This is just plotting the CDFs for us. And we can see that, there is a difference. Not much, but there is. Of course, sampling will change our outputs. And there we can get a 5-number summary going on. So the 5num function gives us a 5-number summary. So these are the numbers that are in a box plot. So minimum, first quartile, median, third quartile, and maximum. 5-number summary. Remember, a box plot is a 5-number summary. So it's just the box plot values. And boom, we can, if I run my box plot values, we can see we get pretty close to each other. All right, now there's some interesting functions that are also available in R. So these are for dealing with the sun. In map tools, we have sunrise T, and we can see that it will give us the fraction of the daylight for the day, and it will give us the time for sunrise, which is kind of neat. So if I give date time and I give coordinates, it'll tell me when is sunrise. You know, kind of interesting. We can also figure out solar noon. There's several functions for this. Solar pause. All right, well, that's all I've got for you. Take care and goodbye.